Good evening, everyone. I'd like to start this presentation with a question. By raising your hand, how many of you have been in math class and have wondered at some point, when am I ever going to use this? Pretty much all of us have, right? And well, it turns out that pretty much all of the math we learn in school and even college has real-life applications. For example, just think about physics, economics, or personal finance. There's one application of statistics and calculus, though, that really piqued my interest. That is population growth models. I always wondered how politicians and journalists were able to know in advance what the future population of a given region was going to be. And after doing some research, it turns out that there are three widely used methods to make such estimates. The first one is the so-called exponential model. Now, some of you might recognize this model because it's commonly taught in high schools and also because it's the simplest one of the three. It combines three growth factors, which are fertility, mortality, and migration. And when you throw those three factors into an equation, you get a graph that looks like this. So as you can see, this model predicts that the population will grow in an exponential way in the future, which makes sense if we consider past population graphs. For example, this is how the world population graph for the past 1,000 years looks like. And it looks pretty similar to the exponential model. But the problem with this method is that it assumes that the population will continue to grow in an unbounded way in the future. And that's a problem because at some point, we're going to run out of natural resources and land area, right? So to solve this problem, let me introduce you to the second model, which is this adjusted or bounded exponential model. If you're curious, the actual name for it is the logistics model. And the only difference it has with the previous one is that it considers a fourth factor, which is the carrying capacity, or in other words, the maximum population that a given region can sustain. And a population graph with this model might look something like this. So as you can see, the first part of the graph looks pretty similar to that of the exponential model, but as the number of people grows and approaches the carrying capacity, the growth slows down significantly, and the population continues to grow, but at a much slower rate in order to stay below the carrying capacity. And we've seen this happen in real life in the past, most famously with China's single-child policy. They were afraid that they would soon run out of natural resources and consumer goods if their population kept growing at the same rate. So they prevented the population from having more than one children in order to slow down the population growth. Now, in theory, this model is much better than the first one, but in reality, it's very hard to make accurate population projections with it. And that's because it's almost impossible to determine with precision the carrying capacity of a region, because there are so many factors that come into play, such as available land area, energy consumption, and even food reserves. Just to give you an idea, the estimates for Earth's carrying capacity vary from less than 1 billion people to over 1 trillion people. So there's a very wide discrepancy between those estimates, and needless to say that the experts don't agree at all on this subject. So this leads us to the third method, which is called the cohort component method. Now this is like the holy grail of population models, and it's the one that most experts use to make population projections. So as its name suggests, this method involves separating the population into cohorts or categories by age and gender. So for example, you'd start with 0 to 4-year-old males and 0 to 4-year-old females, then 5 to 9-year-old males and 5 to 9-year-old females, and so on, until each individual is part of a cohort. And then we consider the same three factors as for the exponential model, so again, fertility, mortality, and migration, but this time for each specific cohort. And this makes a lot of sense when you think about it, because 75-year-old women don't have the same fertility levels as 25-year-old women, right? And in the same way, 95-year-olds don't have the same mortality levels as 15-year-olds, at least hopefully. So in some ways, you could say that this is like an exponential model, but on steroids. Because when you think about it, both methods consider the same factors, but the fact that the cohort model separates the population into categories instead of considering it as a whole makes it a lot more accurate. However, like the exponential model, this one unfortunately does not consider the carrying capacity, which means it might not be the best method for long-term estimates. But still, for most relevant purposes, it is by far the most accurate one that we have. But right now you might be thinking, but why do we bother with trying to predict future population growth? I mean, it's fun to think about, but how is it useful? And my answer to that would be, just look at the housing shortages that are going on in urban centers at the moment. If we had accurate population projection methods, we would have known that more people would move to the big cities. And we could have built enough houses to make sure that everyone can buy a home without having to sell their souls. And this population projection data could even be used to design something like an app or a website that tells you in real time how the house prices in a certain region will look like in 5, 10 years. Just imagine how valuable that would be for the general public. And you could also look at the employee shortage that most employers have been enduring for the last several years. And again, with better population projection tools, we would have seen this coming, and companies would have been able to adapt in order to cope with this situation. For example, they could have reorganized the way they operate in order to require fewer employees. Now, you might tell me that some companies did do that, and I would agree with you, but I would argue that it was done more as a reaction to the shortage rather than in prevention for it. And by the way, speaking of businesses, business owners can also use population projection data to evaluate the potential financial upside of operating in one city versus another. And lastly, a third example would be the backfire of China's single-child policy. Because although it did have the desired effect of slowing down population growth, it also had a few unwanted effects, like accelerating population aging, and even affecting the male-to-female ratio in some parts of the country. So it's for those reasons and many more that we bother with trying to predict future population growth, and also with constantly trying to improve our methods for doing so. Of course, there are some other factors that come into play in the few examples I talked about. It's not all about the population model we're using, but also about politics, psychology, and many other social factors. But still, population projection plays a huge role in our ability to cope with shortages and crises. To conclude my presentation, if there's one thing, and one thing only, you need to remember from this talk, it would be this: better population models equal a better prediction of the future. Thank you.